Hello and welcome to another episode of the Elements of Deep Sea Mining. My name is Eric Young. With me today is Oliver Gunasekara, CEO and co-founder of Impossible Metals, a company that is reimagining deep sea mining technology. Oliver tells me how, despite being a nascent industry, deep sea mining hasn't had a technology overhaul since the 1970s. In today's episode, Oliver explains how Impossible Metals designs their technology to mitigate the environmental challenges associated with deep sea mining, including biodiversity loss, sediment plumes, noise pollution, and carbon emissions. We'll also explore the economic landscape of deep sea versus terrestrial mining and discuss the controversies, misconceptions, and trust issues shaping the deep sea mining conversation.
In my view, you cannot have this debate about the environmental impact of deep sea mining without considering how the mining is going to happen, which means the technology. And technology never stays still.
If you are interested in hearing how rethinking technology can change the conversation around deep sea mining, then please stay tuned for this conversation with Oliver Gunasekara. Let's just jump right in with your background. Actually, if you could take us way back, tell us maybe where you grew up and how did you get from there to where you are now?
Yeah, no, I'm really excited to be on the podcast. I'm currently the CEO and co-founder of Impossible Metals, but grew up in the UK, southeast corner, very, very close to London in Kent. I went to school doing electrical and electronics. First job was kind of embedded software engineer, but then I was fortunate to join a startup called Arm in end of 1994 when there was about 60 odd people. And that company became super successful. I think today its market cap is like 150 billion, six or 7,000 people. But I was there for 13 years, initially in the UK, kind of driving the mobile strategy, promoting ARM technology into mobile. Then I did that in Japan for a couple of years, then came back and ran, I was the director of the mobile segment, really promoting ARM technology to handset manufacturers. And then my last job, I was the VP of corporate development, where I was looking at both investing and acquiring startups. And in that role, I got to relocate to Silicon Valley, where I've been now for 20 years, founded a few other companies in the semiconductor space. And then in 2020, I founded Impossible Metals.
Okay, great. And so you have come, actually like myself, kind of relatively recently to the deep sea mining space. And you came from tech, and I guess you kind of had a lot of options for what to do after you got out of your last business. So why deep sea mining?
Yeah, I didn't know anything about mining, deep sea, or the two together. And for me, it was really driven by the climate crisis. So I was living here in the Bay Area, Silicon Valley. There were really bad wildfires in the fall of 2020. And that got me thinking that maybe I can do one more startup, but it needs to be in something that's really helping us decarbonize in the energy transition. And because it was COVID times, I wasn't really traveling, wasn't really working, had lots of time. And so I was researching. And I came across this company called Deep Green. They're now known as the Metals Company. And I got really fascinated by these polymetallic nodules, these potato-sized rocks that live on the ocean. But being a technologist, I was as intrigued, maybe more, with the tech. When I looked at the dredging tractors and riser systems, I kind of went deep and I discovered that there were patents from 1965 on the dredging tractor. And not only did they patent and invent this architecture, they actually tested it in the 1970s in the deep ocean. And it seemed really bizarre to me that now, over 50 years later, we're fundamentally using the same architecture. And shouldn't we be using more advanced modern technology? With my last company, was in the semiconductor space, having now lived a long time in Silicon Valley, a lot of exposure to robotics, computer vision, AI, batteries. And so it seemed to me that there would be an opportunity to build a newer type of technology that would lower the environmental impacts, lower the cost, and be more reliable without single points of failure. And so that was the original idea for Impossible Metals.
Yeah, no, that's it's amazing that the technology that they're using, or talking about using in the other companies is essentially 50 years old in some ways. Yeah, so I first came across you when you presented your technology at a conference in Bergen a couple of years ago, and it's always stuck in my mind whenever people talk about the environmental impacts of these dredging and the sediment plumes and everything that's associated with the kind of standard large vacuum machine that goes along the seafloor, kind of sucking up everything and leaving very little behind. I always wondered why there isn't more innovation. And so I'm very excited to have you kind of explain what your technology is about and how it works. So.
Yeah, very, very happy to do that. But before I do, I do think there is obviously a lot of opposition to deep sea mining. And the first thing, you've got to break it into the 4 different types. They all have different impacts. And, we're going after the nodule. So in my view, this would be by far the least impactful because there's no cutting or blasting or tunneling. These nodules just lie on the seabed floor. So that's the first thing I would say. The second thing I would say is that you can't talk about the impacts from an environment without describing the technology. The two are intimately linked. So, an example that I like to use is that many decades ago, people considered terrestrial land mining with nuclear bombs. Fortunately, it didn't go anywhere. No one's doing it. But clearly, the environmental impact from that style of mining would be vastly different. And so, in my view, you cannot have this debate about the environmental impact of deep sea mining without considering how the mining is going to happen, which means the technology. And technology never stays still. We are not using the phones of 20 years ago. So you've got to be in the moment talking about what tech is being considered and what impacts, and you cannot isolate it. And that to me is a little bit strange that we hear this strong opposition, but it's based on the technology that, yes, was tested 50 years ago, but doesn't necessarily mean it's the technology that will actually get commercially deployed. So that's my first kind of preamble. But now let me describe how our technology is different. And maybe I can describe for the audience how it came about. So we had this idea, as I described, that we could use modern technology. But we decided as a small core team of engineers to go to first principles and to basically break the problem down into 3 major components. How do you collect off the seabed? How do you move up the water column? And how do you get the material from the surface of the water to a ship and then to a port? And we basically iterated on many different ideas. For instance, in the vertical transport, of course, we looked at the airlifting, the pumping lifting. We looked at drop weights. We looked at a mechanical ski lift style system. We looked at airbags. We looked at using a vehicle that put the material inside and went up and down under battery power, which is ultimately what we selected. But we iterated on many different areas, and we did the same for the collection and same for the transport. And we scored these ideas on what would be the environmental impact, what would be the cost, the economic, and what would be the reliability of this type of architecture. And that ultimately led to the architecture that we've now developed.
So you really started from scratch. You didn't take the existing technology and think, how can we modernize or improve this? You started with, and you started by hiring a team of engineers who were likewise interested in addressing this particular problem, and just kind of sat everyone down in a room with a blank sheet of paper and said, let's get to it.
Yeah, absolutely. First principles, Jason Gillingham, who's our co-founder and chief technology officer, he drove this discussion. He really hired the key people as well. And that was the first thing that we did. And we also were able to attract some incredible advisors that helped us. And so we actually presented, initially, I can give you a bit of insight. Initially, we were going to use a tethered system where our AUVs would actually have a tether. It would simplify. You don't need a battery. It simplifies controls. But one of our key advisors said, think about scalability. You're going to need hundreds of these ultimately. If you want to get to the volumes that become material, that's just not going to work. And so we went back to the drawing board and came up with a fully autonomous system, which then meant we had to invent our own propulsion system because thrusters are not efficient enough. If we were using thrusters and battery power, it would never work. So we came up with the buoyancy engine design, which is a unique design. So that's the iterative first principles design methodology that we ultimately adopt.
Okay, great. So then explain, I mean, I imagine that you're still in the iteration process. You're still developing. You're not at the finish line with the commercial product, but you're very far along and you've got, I guess, what you expect to be the system, and then you're going from here to commercial scale. So go ahead and describe kind of where you're at.
Yeah, the architecture is now fixed. Obviously, nothing can stay still forever, but the first production architecture we fixed on about 3 years ago, and we're now working towards scaling that to a size that can be meaningful. So this architecture, we think, will definitely work really well in production, and then in the future, maybe there'll be other updates. But now this is the approach. And let me describe it. So instead of using a dredging tractor and a riser system and a production support vessel and a dewatering system, a discharge plume and a ship-to-ship transfer, we threw all of that away. None of that exists in our architecture. What we keep is the transport ships. We still need to move the material to port, but we add to those transport ships a smart launch and recovery system. So this is a crane that can place one of our autonomous robots into the water and get it out of the water. And we've invented some unique technology to enable that to happen very quickly and to operate a wide range of sea states. We then add our fleet of robots onto the ship. These robots are about the size of a 20-foot shipping container. They have an array of 12 robotic arms, and they have a 4 metric ton payload. And the rest of the space is buoyancy and engines and battery and controls. And these vehicles get placed into the water, and then they use their battery and buoyancy system that we designed to dive. They dive to about 1 meter above the seabed floor. They never actually land. And then they turn on their array of stereo cameras where they look at the seafloor, and they're looking for 3 things. They're looking for the seabed. They're looking for polymetallic nodules, which is what we want, and they're looking for anything else. And anything else we assume is life. We don't need to train the AI model that's doing this. We don't have to say it's this species of coral or sponge or this type of octopus or these octopus eggs. We just have to say this is not seabed, this is not a nodule. And if we detect that, we quarantine the area, put a circle around it, and we have a do not disturb. The vehicle will fly over the top of that area, and it won't disturb any of that area. Now, if we see nodules and there is no life that we can recognize, the mechanical arms under control of the stereo cameras and the AI algorithms will pick up the nodules one by one, but very, very quickly, place them on a plate at the bottom of the vehicle, and then we have an internal conveyor system that also cleans the nodules. Even if there's a little bit of sediment on them, it will wash them and place them inside the hopper, the storage facility of the vehicle. Once the vehicle is full, it takes about 20 odd minutes to fill the vehicle. It then uses its battery and buoyancy system to float to the surface, where it is then recovered with the automated launch and recovery system placed on the ship. The payload is emptied. Battery is swapped to one that is now fully charged. Any maintenance is performed, and now this vehicle can be redeployed. And we have something like a 3-hour mission time. So every 3 hours, over 7 times in a 24-hour period, one vehicle can be deployed and deliver 4 metric tons of nodules. And obviously, the more vehicles, the more nodules.
Wow. Yeah. Okay. So I have so many questions. So let's start with this buoyancy engine. Are there any other technologies that employ that? I'm just thinking there's not that many operations that happen in the deep sea aside from kind of one-off specific send a submarine down and back up. Did you have to design this system also kind of from scratch?
It's a completely unique proprietary buoyancy system. We have multiple patents on it. I can describe it at a very simplistic level. It's basically a sphere that contains a small bit of air and the rest is water. And we can pump more water in or take water out of the sphere. And so by having multiples of these, we can trim the vehicle, but more importantly, at default, the Eureka 3s, which is the production size vehicle, the 20-foot shipping container vehicle, it is designed to be neutrally buoyant without any payload at the surface. By default, the vehicle will just float. If we need it to sink, which is obviously what we do at the start of the mission, we pump water into the buoyancy spheres, making the vehicle heavier, and so it now dives. And it dives quite rapidly because speed is very important to us. Now, as we get closer and closer to the seabed floor, we use a technology called a Doppler velocity log, or DVL. It's an off-the-shelf component that gives us very altitude using sonar. So we know precisely to about a centimeter how high we are above the seabed floor. And as we get closer and closer, we start to slow down. And we never want to touch the seabed floor. So we are always at least a meter or so above the seabed floor. So we never land. And then we basically get into a neutral buoyancy. So we've pumped enough water in so that the vehicle at that depth, with the current mass that it has, is completely neutral, meaning it floats a meter above. And then we release the arms and they then start picking using the camera. Now, each time you pick up a rock, the vehicle is getting heavier.
Right.
So we have to offset the weight, the mass of the nodules from the buoyancy engine. Otherwise, the vehicle would sink. And we don't want it to sink. We want to keep it neutral. So each time we pick up a nodule, we estimate its mass and we pump out the corresponding amount of water, keeping the vehicle neutral. And we do that constantly as we're picking. Once the picking is complete, just over 20 minutes or so, the vehicle says, right, now I need to go back. And so now we pump out the majority of the water and the vehicle becomes lighter. And so it floats quite rapidly up to the seabed floor. But we do have thrusters on the vehicle so that we can move horizontally, but those are not so power efficient. And those thrusters are very high on the vehicle, a long way away from the sediment. So we want to minimize sediment disturbance. We also have control surfaces on the vehicle. So like flaps on a plane. So we can steer the vehicle as it moves up and down the water column because we don't have to launch and recover the vehicle at the same location. All the vehicles are always in constant communication with the ship using acoustic modems. So we get AD position and status every few seconds.
So when the vehicle reaches the surface, it doesn't have power to go and find the mothership. The mothership goes and collects the vehicles at the surface.
So the vehicle doesn't quite get to the surface. It gets to about 5 meters below the surface, and the vehicle is steered towards the ship because it knows where the ship is.
It does have enough power with its thrusters to navigate to where it should go.
Absolutely. And that's why we have the control surfaces, because they are quite efficient at steering as well. But you know, the Eureka 3 size vehicle has, I believe it's a 125 kilowatt hour battery pack. So larger than an average Tesla size. And that's what's powering. And all the battery has to do is last one mission with a little bit of margin. So, because we're swapping the battery every mission. And so let me describe how the smart launch and recovery. Now, traditionally, you recovered these types of robots with a manual crane and a person would try to hook on, and it could take up to 30 minutes to actually do that. Now, in our economic model, that would be wasteful. We would not be able to utilize. We want to recover the vehicle in minutes. And so we invented a new technology we call smart launch and recovery. And it relies on having another robot on the end of the crane. And this robot has thrusters and it communicates with our Eureka major robots. They communicate acoustically with each other to find each other. And then as they get very close, they communicate optically. And they do a subsea dock of a smart hook below the wave affected area, typically about 5 meters.
Oh, so that's why you don't come to the surface. I see. Yeah.
Yeah. And that allows us to simply do that dock because the wave affected area is very difficult to do docking because you have all of the movement. But if you're below it, it's a lot simpler. It also means that the transport ship does not need dynamic positioning, DP, which is something that you don't typically find on transport vessels, would be very, very expensive to add. It would consume a lot of fuel and would make a huge amount of noise, which would affect marine life. So we avoid DP. That's a big problem for the dredging architecture because they have to do a ship-to-ship transfer. And I don't know how they can do that without DP on the transport, or they're going to have to use another third ship as a shuttle. So that's a major problem that I don't think they have fully understood. But in our case, because of the smart LARs, we avoid the whole need for DP, and we can operate in a much wider range of sea states. And so that really helps our unit economics because we're doing the docking below the wave affected area and we're fully automating it, we can operate in much worse sea conditions, which means more days of operation, which means much greater unit economics.
That's a question I haven't actually ever thought is there a season, or is there expected to be a season for nodule harvesting for some reason, the weather window or something?
So there will definitely be, we estimate for the dredging architectures, maximum they'd be able to operate is maybe 200 days a year out of 365. Because we know in the Clariton-Clipperton zone that the waves are quite severe for many, many days. And with a dredging riser system physically attached, even with dynamic positioning, there's a limit to when the waves get too big or the winds pick up too much that they just will not be able to operate safely. Our system, we think we'll be able to operate, I think the number we have in our model is around 320 days or something. There will still be 40 odd days in a year where even we can't operate.
And that's weather.
There may be some day where there's a tornado, in which case the vehicles would dive and the ship would leave the area for safety reasons.
Fascinating.
And imagine a tornado happening, and with a riser system, it can take a while to recover their system, because it's huge. It's going to delay them for probably a week or maybe 2 weeks if they have to disconnect. Whereas for us, we just tell the vehicles to dive, we can leave them in the ocean, and the ship moves out of the area. So the disruption is going to be far less.
Yeah. Since I've first seen your system and then subsequent discussions, it occurred to me that this kind of floating, I think of it kind of like a floating dump truck. Like you load up and then it just, by buoyancy, goes to the surface. It's so simple, and it's also what's used in traditional mining operations. If you look at the biggest mines in the world, they're not pumping up their ore, even though they've got to travel similar distances from the bottom of the mine to where the ore's destined. They just make big trucks and haul it kind of in one payload at a time. So, okay, so I guess a nice way to maybe go through this one more time is the way that you've got it on your website. You first kind of lay out what the potential environmental harms are of deep sea mining, and then you discuss how your system was designed to address each of those in order. So maybe that's actually a good way, now that you've described in general how your system works, if you want to kind of take it harm by harm.
Yeah. So we have a pretty comprehensive frequently asked questions on our website, impossiblemetals.com. One of the questions we have in the environmental section B in the website is what are the potential environmental challenges with deep sea mining? So the first problem we see is the loss of biodiversity. I mean, if you're ultimately destroying all of the life in front of your collector, and you're removing all of the nodules, and we know lots of the life need the nodules, then you're going to have a big problem here. And also, if you're generating a large plume, that potentially has a problem. And so, our approach here is to leave behind a percentage of the nodules. In our economic model, we assume 30% is always left behind to maintain the ecosystem viability. But that's a number that we can arbitrarily change. Software on the vehicle, it's very easy. And it doesn't drastically change our economics because the nodule fields are so abundant and so large. But we think 30% is pretty good. So obviously included in that 30% would be any of the megafauna, the life that is above a millimeter in size that the cameras can recognize. But we can't recognize bacteria. We can't recognize smaller organisms. And so that's why we've chosen an arbitrary number of 30%, which could well change. And that will always be there, preserved. So this is the first time ever, in my view, that we are able to do mining, but to preserve a portion of the habitat at the same time and keep it viable. And I think that's really massive win and something we care a lot about. The second is the sediment disturbance. Now, our vehicle doesn't land. It has no tracks. It has not injecting water in the front of the vehicle and then sucking it up and then removing the water on the ship and then pumping that water back into the mid-water column. We're not doing any of that. So the only disturbance that we will have is as we physically pick. And there will be some disturbance. The sediment is quite loose, but that, in our view, is going to be significantly less. And we have a mathematical model. We want to do trials. We want to quantify it. We will get there. But our belief is that it will be significantly less than the plume that is generated from the dredging systems, just because the vehicle is hovering. And by maintaining that neutral buoyancy, the only disturbance is, as I said, as you physically pick. And right now, there are some videos we've shown there is definitely disturbance even in shallow water, but we've really optimized those videos for speed and accuracy. As we have now started to achieve our objectives on speed and accuracy, we can start to look about, well, how do we adjust the movement? How do we adjust how we actually engage the claw with the nodule? In the current design, we kind of scrape the seabed a little bit, and that generates more sediment disturbance. So I think there are things we can do, but we're very committed to trying to minimize the amount of sediment disturbance we can. The next is noise and vibration. What we do know is that the majority of the noise, even from a traditional dredging system, is going to come from the ship, because the ships have DP, dynamic positioning. These are big thrusters that keep the ship super still, and they generate quite a lot of noise. And unfortunately, this noise is right at the surface, and that's where the big mammals live, the dolphins, the whales, etc., that will be affected the majority by the noise. So we don't have that. We don't need dynamic positioning. We don't have a riser pump, which will potentially have pumps through the water column. That's all not in our system. And so, we will have a little bit of noise from the pumps in the buoyancy system, from the movement of the arms, but that will be, in our view, significantly less, and it will not be predominantly at the shallow water where the big mammals that are affected by noise are. Light disturbance. We do need some light. We only turn the lights on when we're at the seabed, just above the seabed floor, but clearly there will be light pollution. What we're working with is a team of marine scientists to try to understand what is the optimum wavelength that would have the least impact, because we can choose which color we use. So that's something that we're doing. We're also looking at higher performing image sensors. Image sensors, if you look at your phone, taking pictures in the dark, they've got incredibly better, especially with image processing. Mm-hmm. And that's something we can also take advantage of. We haven't yet in the Eureka 2 system, but that's something that we're thinking about, is like, how could we use less light and have more efficient sensors? Again, one of the advantages of our system when compared to other people that do computer vision and AI is that we control the illumination. There is no light down there. And so we're under the control of that. The next is the loss of the hard surface. Yeah, if you remove all of the nodules, where does the octopus that lays its egg on the nodules, or the coral that needs to attach to some hard subsurface, how does it survive? Mm-hmm. And so that's the strategy of leaving at least 30% behind. And then the final one is really the emission of greenhouse gases. We do need energy to power the ships, to power the robots, but we have committed in our system that we will be net zero for all of our production, meaning that in the short term, we're going to offset any emissions that come, or we're going to find a way to capture those emissions to not let them get into the atmosphere. So, for testing to date in the ocean, we've used a diesel generator to charge the battery. Mm-hmm. But, we're looking at newer technologies that are emerging that are greener, or we're looking at offsetting, or we're looking at capturing. But we've committed that by the time we get to production, there will not be any emissions from our operations. That includes powering the robots, transportation of the ore, and mineral processing. And probably in the first few years, we will use carbon offsetting to get our emissions to zero. So those are really the major ones. There is speculation out there that carbon stored in the ocean will be released. That is not true. We know for a fact that almost none of the carbon that is taken by the ocean, which is considerable, makes it to the deep ocean. It's all absorbed in the upper parts of the ocean. And we know there isn't carbon in the nodules, and there is no mechanism for the carbon that's in the seabed to get into the atmosphere. So we don't believe the rule, what some people are saying, that this is a concern for carbon to be released as part of our operation. And we also don't believe that there would be any impact for fishing, because we don't have a discharge plume. And the plume or discharge that we have is going to be localized to very, very close to the vehicle. Now, we need to do more testing, more scientific data to convince a regulator and prove exactly that's the case. But we're very confident that that will be the reality.
Let me just ask about your business model. Is your intention to run the entire operation? Will Impossible Metals be the full mining company, or are you a technology supplier to other companies?
We started building technology, but we feel our tech is differentiated enough that we would like to partner with contractors, people that have exploration licensed areas, and basically share in the upside. Our primary focus is not to sell technology, but to enable a mining operation where we get to participate in the upside. But we very much have what we call a phase 1 and phase 2 strategy. Phase 1 is to partner with people that have exploration areas. As you may know, there are about 40 exploration license areas globally. 31 of them are in the ISA or international waters. The remaining are in local countries' exclusive economic zones. About just over half are for nodules. The rest are for other types. And so many of these contractors have been doing environmental science for 2 decades or more now. They got their exploration areas in early 2000. They've spent considerable time and effort collecting massive amounts of scientific data. Just as a side note, the people that say we know more about the moon than we do the ocean are completely false. They were to pick a random spot on the ocean, that might be true. But if you pick one of these 40 exploration areas where people have done multiple missions, deployments with suites of engineers, thousands of scientists, we actually know vastly more data. And all of this data is open source and published in the deep database on the ISA's website, and also submitted to other biodiversity databases. So our strategy with phase 1 is to partner with people that have done all this scientific work, but don't necessarily have technology. Phase 2 is an area that we're exploring, which is maybe getting our own areas by applying and getting sponsored. But obviously then we are now responsible for collecting that data, and it will take 5 years or so.
And then, I guess timeline. So how far? So your Eureka 3 is now the full-sized collector vehicle, and you've got that in testing.
Not yet in testing. We are in the design phase of Eureka 3. Eureka 1 was our shallow water test vehicle. It could go just 25 meters, but it did have the buoyancy engine, the robotic arm, and AI vision system. Those are the unique IPs or technology that we brought to bear. So we proved that a couple of years ago with Eureka 1. Eureka 2 is the deep water test vehicle, proof of concept, if you like. So this one can go 6 kilometers or over 4 miles deep. It has 3 arms, and we've tested this now at about 2 kilometers in the ocean of Florida. We're now in design of Eureka 3. Now, Eureka 3 is significantly larger, but it has no new technology. It just has more arms, more buoyancy, more storage capability. And this is the size that could go to production. Obviously not one, but a fleet of 10, but in time, potentially even hundreds.
And do you have expectation about when you will kind of reach the TRL that you can do commercial operations, and how How is that lining up with when you expect commercial operations to kind of be green lighted?
Yeah, we kind of feel with Eureka 2, we're at the TLL 5 level right now. We've proven the core technology, but it's on a smaller scale. So Eureka 3, we need to build and test. That's not a small undertaking, especially when you talk about testing in the deep ocean. We hope to do that testing next year. And then once that testing is complete, we then need to build a fleet of these vehicles. And then that means that probably if things go to plan, we will test in 26, build the fleet in 27, go mining in 28. Now, that's completely parallel to the regulatory side of things. So we need to sign a commercial partnership with a resource access vendor. They need to submit an exploitation application. That application has to be reviewed by the ISA and potentially granted. And so the idea is that these two things line up so that in 2028, we could be starting to mine.
Well, it's incredible where you are at, considering you just started looking for something to do during COVID. When I think about how much I've gotten done since COVID to now, it's intimidating. I guess while we're still on your technology, it sounds like the kind of speed of collection is one of the main challenges or goals. And you mentioned that whether you collect or whether you leave 30% or some other number, it doesn't affect your economics so much. But I imagine that the rate of collection, how many dives you can do in a day, is much more kind of central to getting this in the green as opposed to in the red.
Yeah, I mean, if you think of the 3-hour mission time, majority of that mission time is spent moving down or up the water column.
Is that right?
Very small amount of time. We have it in one of our FAQs, exactly how the time is broken down.
Did you also consider having the collector vehicle stay at depth and having a separate vehicle that just was a transport?
We did actually, and there is some optimization to do that, but you have increased the complexity significantly. You now have to design two vehicles. You have to figure out how they dock, how they transfer power. That's a lot more complex. I would imagine that could be a future second major revision of the architecture in 5 years' time or something. But for now, we're really happy with the economics. We're looking at being something like 1/3 of the cost of the dredging and riser systems for the same rate of production. So literally 1/3 of the cost. And what we use there is costing in the mining world that's called the all-in sustaining costs. So we're looking at, for a Eureka 3 system, for a CCZ polymetallic nodule, and this includes both the collection, the transportation, and the mineral processing. We're looking at about just over $1,000 a metric ton. Now, the average cost for mines on land in 2024 was just under $15,000 a metric ton. So we're looking at being something like close to 15 times lower cost than the average nickel mine. And the cost for the dredging is about $3,000. If you look at GSR or TMC's economic data and calculate the all-in sustaining costs, they're coming out about $3,000 a metric ton. So we're about 1/3 of their cost.
This is a metric ton of ore that you're comparing to. A metric ton of nickel.
Metric ton of nickel that you've extracted.
Yeah, okay. Nickel in ore.
Yeah. And if you think that the average cost in 2024, this is Wood Mackenzie data. This is a big mining analyst. They published this data. They said it was just under $15,000. Now the sell price was around $15,000. So you actually see that very many mines, especially in Australia, have closed because they cannot compete. Their cost to get it out of the ground and processed is higher. And so this is why, I think in a previous episode, one of your guests was talking about supply and demand and the economics. I didn't quite agree with some of his conclusions. So one of the key conclusions here is that we don't need seabed mining because there's plenty of material on land. All that needs to happen is that the price goes up and that unlocks more supply. Of course, that's true, but that's not the reason I created this company. I want everyone to be able to afford an electric vehicle. If the nickel price goes up substantially, that will not be the case. In fact, you could argue it's already not the case. So the biggest cost in buying an electric vehicle today is the metal in the battery, and the majority of batteries today are nickel-based. And so the nickel has the biggest overall cost. And your guest is right. With traditional supply and demand curves, if the price goes up, a lot of mines that today are underwater that can't make money will be able to and will come onto the market. But the end result is that the price goes up, which means we can't afford for people to have electric vehicles. So I want everyone to be able to electrify. I actually want the price to come down. And that's what deep sea mining can enable. Because the cost structure, no matter even if you're using the older technology, it's going to be substantially less expensive than land-based mining. And so we will close and stop new land-based mines from opening because of the economics. Just as almost all of nickel mining in Australia today has closed because they can't compete with Indonesian mines, their cost structure. Deep sea mining will do the same. And that's a good thing because we have far less environmental damage and we're not being controlled by China, and we have almost no social impacts. The social impacts of mining do not get talked about enough, but they are quite outrageous.
So, yeah, I don't know if you want to say more about the kind of need for critical minerals.
I would, but I would like to make people crystal clear, why are our costs so much less? Like, put out a number that we think will be 15 times lower than the average nickel mine. People probably find that hard to believe, but I can explain it if that's helpful.
Absolutely, yeah.
Yeah. So the first reason, and in fact, anyone going after deep sea minerals will get this, is to do with the fact that the resource is polymetallic, 4 metals in one, it's unattached, and it's in the ocean. So the biggest economic drivers of a mine are its grade, what percent is value versus waste, how many metals are in the ore, where is the mine, because that means what infrastructure do you need to build to support the mine, and then finally, what do you have to do to reclaim the mine at the end of life? Those are what go into the economic model of any mine, whether it's on land, in the ocean, or even in space. So if you look at new land-based mines, they are always at a disadvantage because the good stuff has already been mined. The high-grade local minerals we mined 50 years ago. What you find today is low-grade, remote. Low-grade means the typical new nickel mine that you're discovering is a fraction of a percent of grade, maybe 0.2, 0.3, 0.4%. The rest is waste. You still have to dig it all up. You have to process it. That compared to 50 years ago, where you could find nickel mines at 4 or 5 or even 10% grade. So the grade has constantly gone down as we've mined all the good stuff. And on land, you maybe get 2 metals together. You might get nickel and cobalt, or copper and cobalt, etc. But you never really find 4 metals, nickel, cobalt, copper, and manganese. That's super valuable because for all the effort, you're getting 4 metals in one versus just getting 1 or 2 on land. And then location. Well, if this mine is in a great location, there's a road, there's power, there's accommodation for workers, that's amazing. Guess what? That doesn't exist today on land. You end up having to go to very, very remote locations, the middle of Africa. You're going to helicopter it. They're going to have to build a road, going to have to build accommodation, maybe even build a railway line, build the power. All of that costs time and money. And that's why the average cost today, according to Woods Mackenzie, was just under $15,000 to mine, transport, and process. We think we're going to be 1,000. Why are we so low? Well, in the ocean, we don't need to build any land transport. We reuse ships and ports. That's the most efficient transportation, and it's widely supported. There's infrastructure everywhere. That's a huge saving. Secondly, we have polymetallic. They're 4 metals in one, and the grades are super high. The nickel equivalent grade in the nodules is close to 4%. Compare that to 0.2% or 0.3%. That makes a huge difference. And then on the reclaiming, well, we're leaving 30% behind. There is no reclaiming. In a big rainforest that you've destroyed, you've got to refill it in, you've got to replant, it's going to take decades, and you've got to pay for all of this. We don't need to do that because we're preserving the habitat. And in our case, we're using fully automated systems that have almost no people, and we don't need a production support vessel. So if you know the Hidden Gem, that's the metals company's production support vessel, that does not exist in our architecture. We've saved all of the costs, the capital cost and the operational cost, because we don't need it and we have more uptime. So that's why we believe in our published economic model, including being net zero at scale, we're going to be about $1,000 a metric ton, which is 15 times cheaper, which means that the Indonesian and the bad mines in Africa will ultimately close, or they will not start new ones because they will not be able to compete with the pricing that we can bring to market.
That's ambitious. And then what about your downstream processing? Does this just go straight into existing processing facilities, or do you anticipate that the deep sea nodules will kind of take over the processing and refining infrastructure that is currently used for land-based minerals?
I think that's the first phase, that there will be some modifications because they're not set up to take exactly this ore type. So there will need to be some modifications, but PAMCO, Pacific Metals in Japan, is doing quite a large test with the metals company. I think they've published they've tested over 2,000 tons of nodules and been able to smelt them using a traditional process. So there is now good data that shows that you can reuse existing. It's probably not as efficient if you built custom infrastructure. So I see that would happen in a later phase.
Okay, so then let's get into a little bit of the pushback and the controversy around deep sea mining. And maybe just you can start by telling what it's like to be in this position of being in such a controversial industry where I think very little is known about it beyond that it's controversial, and that I imagine you kind of get painted with a brush in a lot of rooms you walk into.
Yeah, I mean, it's definitely a big headwind that we come across. As I said, my challenge is that we're being painted with the same as other technologies, and our impacts are being designed to be significantly less. And so, the NGO community is incredibly well financed. We're a small little startup, a few years old, 20 odd people, we're a small outfit. And yet you have the likes of Greenpeace that has, and Pew and WWF that has massive organizations, teams of people, millions of dollars of budget to fight this. They spend much more on fighting deep sea mining than we spend on all of our development. It's a very asymmetric battle that is being fought.
And so do you get an opportunity to speak with those people? Does the kind of arguing happen in the media? And then you also get a chance to talk with people in the restaurants after a conference and lay out your case?
Yeah, and I think we are finding some people that understand our position and are being a little bit more open to it. I mean, fundamentally, I think everyone's coming from the best intentions.
Mm-hmm.
It's what's challenging, though, is that there's this view that because mining has been so bad for the planet, we shouldn't start a new frontier. I understand it. That's I think, the crux of the argument. But I think you need to take a complete look at the problem. And today we mine in some of the richest biodiverse environments known. Rainforests in Indonesia, massively more biodiversity and life than on the deep ocean. And, I'm a big believer we need to protect the deep ocean. That's why we've designed our system to avoid life, to preserve 30%, etc. There is life there. It is very precious. But you can't, in my view, sacrifice one area and say it's okay to destroy the rainforest, which another thing that I often hear from NGOs, look how many undisturbed or what's the word I'm looking for? Undiscovered species in the deep ocean. And there are lots. But guess what? There's just as many in that rainforest. We find undescribed species in rainforests every day. It's as common. So what I find is, why are people so against one area but seem to not care about another? That's what I find is a bit strange. And also this call for a moratorium. I wish they would be honest and say we want a ban, because that's what they want. We've had a moratorium for 60 years, right? Since there is no deep sea mining happening right now. We're only doing the research phase. And this has been going on for 60 years. Before UNCLOS, the UN Convention on the Law of the Sea, was ratified, it was decided to have a moratorium, to have a ban, because we needed to put the rules in place. That was 60 years ago. We've now collected massive amounts of data. We have a robust environmental impact assessment process that all mining companies have to go through. And we think that the regulations need to get finished, the mining code, and let each application be evaluated on its merits. And let's think about, if we say no to the planet's biggest source of these metals, which we can extract with the least impact without the control of one country, we're setting ourselves up for failure, in my view, where we will be dependent on China, which now controls the vast majority of critical minerals. We'll have massive environmental destruction, massive social destruction, and the costs will rise. And it will come to the point where it will not be affordable to electrify everything. And so our carbon challenges will be jeopardized. And so to me, that's the discussion that we should really be having. I guess, again, my biggest point is the technology doesn't enter the discussion.
Yeah.
It's and deep sea mining. But if we were using nuclear bombs, maybe. But if we're using selective harvesting with AI to leave 30%, to preserve the habitat, to minimize the sediment, minimize the noise and light, that's a very different architecture than the things that were designed in the 70s.
One of the ways that I've heard this discussion kind of characterized is that people aren't comfortable making these hard trade-offs. Land-based mining exists, it's happening. And I mean, I guess there's a couple of reasons why the deep sea is scary. It's new and it's got more uncertainty than ecosystems and environments that we've experienced firsthand, etc. But I do think that this question of like, how do we make decisions when we've got to weigh trade-offs between kind of non-ideal outcomes on both sides is something that is central to this discussion and difficult. So I'm very interested in trying to ask everybody who I speak with, how do we best make decisions when there's trade-offs and uncertainty and multiple different value categories? There's economics and there's human welfare and there's unknown ecosystem services that we haven't even discovered yet, et cetera, et cetera.
All of those, Eric, apply to land-based mining as well, right? It's unknown ecological, environmental services. Do you think we know absolutely everything to know about a rainforest? We don't. So all of the reasons that people put for saying that we have to know everything, and you're a scientist, you'll never know everything, there's always more to learn, can be applied to any project. If you say, I need to know the complete sum of all knowledge over all time for this subject, you will do nothing because it's impossible. So you have to make decisions without knowing everything. That's how life exists. We always have to do that. And it's not to do with deep sea mining or land mining or anything. You never know everything. And the way you do it is you have a robust environmental evaluation. You have the rules that are put in place, the mining code. And, I think a lot of people don't realize, the industry is working really hard to put a mining code in place before any mining happens in the ocean. That's never happened before. Normally, the regulations are catching up after something happens. But that's not the case. Like, there is no mining yet. We've been working on it for 60 years, working on the rules, starting with the law, the UN Law of the Sea, 1982, the ISA, established in 1995, the mining regulations, the exploitation regulations adopted 20 years ago, the draft of the exploitation regulations, first draft a decade ago. We have been having a moratorium for 60 years. Or in that time, we've been collecting huge amounts, probably $1 billion has been spent on marine science, collecting data, publishing data, making it available. We know a huge amount, and we have this robust environmental impact assessment that means that any mining would have to be evaluated against what is going to be the impact. And that's the whole point of the regulatory authority. And we need to finish the rules and let the regulatory do its job. And does that mean we're going to know absolutely everything? No, they're never going to know everything. But that's true about any project anywhere. But we are going to know enough to be comfortable that we're not going to do any serious harm. And I hope we're going to consider how new technology like the type that we're building can even reduce that impact significantly.
Yeah, well, I think certainly in these kind of discussions, the details are very, very important. And I think people enjoy having the discussion at a higher level. And like you say, you have to bring in not only all the data that there is, but then also the technology. I think that's a good point. Bring in the technology, bring in what we're talking about in the specific case. And I think what you said also about the distinction between a moratorium and a ban, and also just the distinction between a moratorium and what industry actors like you are advocating for is actually quite thin. I mean, I think everybody is advocating for a system in which mining doesn't happen until we have a good environmental assessment process in place. And in Norway, anyway, I think that when you talk to people who understand the details, about the details, what it comes down to, essentially, this is my opinion, is a trust issue. It's like, we all agree on what the framework should be, but then at the end of the day, we're going to have to trust that the rules are followed, and that if after you spend 10 years and millions of dollars developing a technology that works, if you find in your environmental impact assessment something that ought to be a showstopper, but is 6 kilometers deep and you're kind of the only people who have access to it, there's a trust issue there. And certainly that trust issue is I mean, again, it's there in mining. People don't see what's happening in all sorts of industries, but I think that trust is one of the main kind of bugbears in the conversation that is maybe not often talked about directly enough.
Yeah, I mean, you have to trust the regulator will do its job. I mean, the environmental impact statement, which is the key document, very comprehensive. It should cover all of the impacts, and it should then be verified. And, if a mining company didn't disclose an impact, they should get the license withdrawn. I mean, that's how things are. But, I do want to touch on this moratorium. One of our colleagues wrote a blog post on it. It's described by NGOs as why deep sea mining shouldn't happen. We got 32 or 33 countries that have signed the moratorium. But as you said, the moratorium describes what we're doing. It describes and says there should be no mining until the regulations are created and an environmental impact assessment is carried out, and it's confirmed that there is going to be no serious harm. Well, that's exactly what the legal frameworks are. So anyone signing the moratorium is supporting the frameworks that have been developed. And in fact, all they're saying is we don't support illegal mining, which is obviously a form of mining that doesn't go through any of this. And fortunately, there's none of it in the sea, but there's a large amount of it. In some regards, in some countries, it can be as much as 30% is illegal mining that has none of this, and a lot of corruption, a lot of bribery, huge environmental and social damage. We actually think that everyone should support that statement, but it's not how the NGOs use it. They use it and say, well, this and so country has signed up to the moratorium, so they're against deep sea mining. That's actually not the case. They're against illegal mining, but they're for what the frameworks have been adopted. They're for legal rules being created, a mining code being created, environmental impact assessment being carried out, and it being reviewed by the regulator and confirming that no serious harm is going to be generated. So again, we feel that that is completely dishonest by promoting all these countries that are signing up, because what they've signed up to is what is actually happening. And if an NGO doesn't want it to see deep sea mining, say they're for a ban. Don't say they're for a moratorium, because I think if you were to ask Greenpeace or WWF or Pew, do you want a ban? If you could choose a ban or a moratorium, which would you pick? I think they definitely would pick the ban.
That's interesting. And that is something that I intend to ask. And actually, I had a conversation with someone this morning, and I'll release that conversation. I'm not sure if it'll be released before or after hours, but she was quite open that their organization is in favor of a ban.
Yeah, good. I respect that. I mean, I don't support it personally, but it's, for me, far more honest to be transparent and say, we're supporting this. Because, as I said, the language of the moratorium is exactly what the industry is doing.
Do you have any idea of why there's been so much attention around this?
I have a theory. I don't know if it's true, but I think the trigger of the 2-year rule by Nauru on behalf of the metals company, I think really upset the NGOs. I feel there has been a change since that. And I think no one really wants mining to go ahead without the adoption of the mining code. We don't. We want strong regulations, but that's my feeling. I don't really have hard data to back it up.
Yeah.
I've seen a change. I think it was 3 years ago that the 2-year rule was triggered.
And that makes some sense. I guess for people who aren't super familiar with this, the International Seabed Authority that is trying to develop the regulations that will govern how mining happens in international waters has been taking a long time to get the rules in place. And somewhere in their convention was a paragraph that said, if anybody, I'm not sure exactly what you have to do to trigger the 2-year rule, but
you just have to say, I'm ready to go mining.
Mm-hmm.
And I mean, again, let's just back up a little bit. This is in the UN Convention of the Law of the Sea, so it's an actual part of the law, and it was put in for exactly this scenario. They imagined a scenario where a bureaucratic UN-created body might take a really long time or not able to get the mining code complete, and yet a contractor that has invested considerable time and effort wants to go mining. It can give a 2-year notice. So any contractor that says they are ready can give a 2-year notice that says the ISA, you need to now get your mining regulation complete within 2 years. Or if you are unsuccessful, then they immediately have the authority to submit an exploitation application that would then be considered under the draft regulation. And so that's the scenario that we are currently in. Because the 2-year rule was triggered, any contractor that has an exploration license that wishes to submit an exploitation agreement is now not legally required to wait for the mining code to be complete. It can be submitted.
They can submit, but the council is now then considering these applications kind of one by one. So it's not that after 2 years, they can go ahead and start exploiting. There's still...
Yeah. There is some ambiguous text that I think that in the law says something like you can submit and would be provisionally approved. I think there is some drafting around that. So it's a bit unclear exactly what does that mean. But in all cases, even after the rules are adopted, the council has the decision to decide if an application is granted or not, just as they do today for exploitation. It's not like the exploitation regulations were adopted 2 decades ago, the mining code. And obviously many companies have submitted. It's not that you automatically get an area. In fact, some have been denied. You have to submit an application and negotiate it in front of, I forget if it's the LTC or the council, but one of the organs of the ISA. And only if you're successful do you get awarded even exploration rights. Right. And the same will be true for exploitation.
And so the next session of the ISA is next week in Jamaica.
I'm going there for my first time, actually. So I'm quite excited to officially attend.
Yeah. That'll be interesting. Yeah, I guess that there you'll have lots of opportunity to bump elbows with the NGOs and others and try to make your case and to hopefully
we're actually,
bring down some of the...
Yeah, I'm excited. We are jointly hosting a side event with the ISA Enterprise on Tuesday. So I don't know when you'll publish this, but I believe it's Tuesday the 18th, 3 p.m.
We should be able to get this out before that.
Right. Yeah, we have an official Impossible Metals with the Enterprise. And I don't know if people are familiar with the Enterprise, but it's one of the organs of the ISA that allows the ISA to be its own contractor. So again, it's a little bit unusual, but it's in UNCLOS. And so the Enterprise doesn't need a sponsor state. It has the ability to be its own contractor. It actually has some preferential treatment, like it gets first rights on any reserved areas. And I believe it also has some preferential treatment on the royalty situation. And so that's an interesting quirk of the ISA.
Well, I'll have to get someone with real expertise in the ISA and its workings on for an in-depth discussion, because I feel like there's a lot to cover there. Okay, Oliver, is there anything else that you would like to cover before we wrap up?
No, this has been great. I think one thing I would touch on is the recycled content. I mean, a lot of NGOs will say to me, well, we don't need deep sea mining because we can recycle. And in theory, that's great. These metals are recyclable, which is unlike oil and gas. But if you look at the IEA, the International Energy Association, recycle forecasted rates for nickel, for instance, which is probably the most valuable metal we would be harvesting, by 2030, they are forecasting of all demand for nickel, 3%, 2030, in 5 years' time. And in 2040, 10% will come from recycled or secondary use. So in 15 years from now, in 2040, 10% of forecasted demand will come from recycled or second use material. 90% comes from primary mining.
Yeah,
I think it's clear that recycling is not a solution for the next 20 to 30 years. It doesn't move the needle.
Yeah, certainly with the projections, if electric vehicles continue to increase market share and then continue to be reliant on nickel the way they are, that's currently they use the recycling rate of 64% is what the modelers use for nickel, or is what they think is currently recycled. So even if we were to get that number up to 100% recycling, you just can't meet a growth demand with recycling at this stage.
And remember that the vast majority of nickel today doesn't go into batteries. I think less than, if I remember correctly, less than 20% of nickel production today goes into batteries. Majority of it goes into stainless steel and alloys and other infrastructure. So even if battery chemistries change, which I'm very skeptical on, LFP is a Chinese focused technology. It's significantly heavier. You have about a third less range. So, for China, where they have a high-speed rail network and they don't need long range, it's a perfect fit. But for Europe and North America, where we have a lot of road infrastructure, long range, nickel is by far a better chemistry in my view. And if we can drive the costs down, I think we can actually make the nickel chemistries cheaper than the LFP or the iron phosphorus. And so that will affect, even if you don't buy this story, nickel's used in all these other markets. So there just isn't enough material coming end of life to recycle in the next 20 to 30 years. So we got to do new mining. And then, other people will talk about substitution and reducing demand. We've written about this in our FAQ. I don't think it's realistic. Like in North America, where I live, there's almost no public transport. You have to have a car. You have to have multiple cars. So it's a bit like saying the whole world should go vegetarian. It would be better for the planet and maybe for people, but you're just not going to get the majority of people to give up meat. And same with cars.
Yeah, that's what I was going to ask you that, because I could hear that the pushback to, I want to bring the price of an EV down to where everyone can afford it. The pushback obviously as well. Everyone doesn't need to have an electric car. We can get by with I mean, I've got a couple of electric bikes and we have one car that we share between several people and so on.
Yeah. But different countries have different infrastructure and different needs. And it's not just the cars. As you said, it's the two-wheelers as well.
Mm.
And fundamentally, the climate crisis is the thing that's going to affect everyone the most. Actually, I think it's the biggest threat to the deep ocean. So if we don't get these metals and we're not able to reduce the amount of carbon we're pumping into the atmosphere through electrification across a whole range of industries, then the deep ocean is going to suffer hugely. And so I think that's another reason. And I also don't think it's fair to say to the developing world, say in Africa or India, you can't have an air conditioning unit because of the minerals that will be used or the power that will be needed to power it or to transport the energy. So I think it's an ethical concern that just because we in the West have got all of these luxuries, we shouldn't say to the developing world, you can't have them because of the environmental cost to get the minerals out of the ground, which is why I don't believe we can drastically cut demand, and I don't think we can substitute. So I think we have no choice, and we can't recycle enough in time. So we've got to get these metals from somewhere. If we continue to get them from land, we'll have massive environmental, social destruction, and the prices will rise. If we get them from the ocean, with our tech, we can preserve a lot of the ocean, drive the prices down, have no social impacts, and also avoid some of the geopolitical risks that we're running into with China now controlling the majority of these metals.
Okay. Well, this has been very interesting and great to get more details on your technology, which has, like I said, has been in my mind since the first time I've seen it. So I hope that you get more attention to that. And are there other, I'm not sure, maybe this is the wrong question to ask, but are there other companies also developing similar alternative technologies, or is it basically the large vacuum with the riser stack and then you guys?
The only thing I've seen tested is the large, dredging tractor and riser system, and there's maybe 7 or 8 companies. There's 2 Chinese, there's a couple of European, some Indian, some South Korean, but I haven't seen anyone else test anything else. But I think we're the only company that has done ocean testing of something else. Maybe people have pencil paper designs, but we're the only ones that have actually done the testing.
I mean, I guess it's a pretty ambitious and a kind of a long haul. You've got to commit early, and when you got into this, you must have known you're looking at least years before being able to commercially deploy.
Yeah, but nothing that's worth doing is easy. We really think we can make a difference in how the world gets these critical minerals and accelerate electrification. I think that's a worthy thing to do. And everyone in the team is really passionate about this mission and doing it right. And I think we try to be really transparent and open and publish data in our FAQ, on our website, on our YouTube channel. And I'll give you links for the show notes if people are interested. But we're trying to be different. We think of ourselves as a 21st century mining company that's really using technology to minimize the impact and lower the costs.
Well, that's a great place to sign off. So yeah, so just quickly tell people where they can look you up and follow you.
Yeah, I mean, our website is impossiblemetals.com. That's where we host most of our material. We have a YouTube channel with the same name, and we're pretty active on LinkedIn. Those are probably the best places to reach out, and anybody can reach me. I'm Oliver at impossiblemetals.com if they want to have a chat.
Okay. So, Oliver, thanks so much for your time.
No, thank you. That was great.
I threw my arms up and to the side.